So from the last class, we have derived that the simplified form of the diffusivity equation. We only finished up to how we get the simplified form, but we haven't really solved it. And the equation goes by 1 over r times partial over partial r partial p partial r is equal to the compressed porosity, viscosity, and the compressibility over permeability times partial p partial t. To get this equation, we had several assumptions. First assumption was homogeneous and isotropic rock property, meaning K is constant, porosity is also constant. And the second assumptions that we'll need to the equation up to here is that we assume the radial flow that has and then this radial flow goes all the way up to the entire formation thickness. So basically, we assume the reservoir goes by this shape, and we have a well in the center, and the pressure diffuse in a radial direction. So fluid goes in a radial directions. And then the third assumption was we assume that saturated by single fluid. Typically, in the conventional way of thinking is it's only filled by a hydrocarbon, maybe single fluid. And then it's not written in the book, but it's quite obvious that it's isotropic. No, isothermal. There might be heat gain or heat loss in the processes, but we assume there are abundant heat source and the heat transferred instantaneously. So throughout the process, we assume they are isothermal. So the pressure is varying, but the temperature is equal to any location. And we also assume this compressibility is also constant. This may not be true. When it comes to a gas flow, so this will be covered in the later chapter of the book. And we also need a further assumptions, which is the constant viscosity. So viscosity also assumed to be constant. Again, this may not be also true when it comes to the gas state. And then the last assumption that we need is partial P over partial R is small, so partial P partial R square is equal to mean is a negligible. So we needed this R7 assumption to get this simplified form of the partial differential equation. And there are three different conditions. Let's talk about the conditions. So the first condition is transient. And the second condition is after these pressure changes propagate up to the boundary of the reservoir, we may meet a aquifer or not. If the reservoir is cut by the fault or closed boundary, then there's no further pressure gain from the boundary. So we are constantly losing the pressure. That's the semi-steady state condition. Otherwise, we may end up with aquifer, or we have this secondary production, meaning if we have the influx of the fluid from injection activity, then that can be also steady state. As I told you in the class, steady state is simplest one because it's a matter of ODE, so the time doesn't matter here, but the transient and the semi-steady is PDE. And among these three, the most challenging part is this one, and we are about to cover this transient partial differentiation. We are going to find the solution for the partial differentiation. So here, to simplify above a equations, we are going to define eta. Eta is equal to K over porosity, viscosity, and then the compressibility. In the book, the book from the Dake, it says it's a capital T, but I think the eta is a more widely used, so I'm going to use the eta instead of T. So if eta is defined as such, then the above equations can be written as this. I simply expand this partial R into this term, and then using this chain rule, I could make it in a two form here, then two terms here, and the right hand side it's simply we've just replaced this as 1 over eta, and that's how we get this equation. So to solve this equation, we need three additional conditions. First, we need an initial condition, which is P is when the time is 0, the initial pressure is constant as the initial pressure. And there are two boundary conditions. So let's say we have where in the center, and then we want to have the plot of the pressure in this direction, and then the x indicate R. Then we know that the pressure in the beginning was pretty much constant, just like PI. Then once we start to produce the fluid, then we know that the pressure will be varying like this, right? So the pressure will be decreasing, but this is when T is a T1, T2, T3, and so on. So so we need a two boundary condition. One in the right location of where the wellbore is located, and then the second boundary condition is where this, the infinite distance. I mean, so while there is transient flow is occurring, when the distance is going to infinite, then we can also know that the pressure is equal to the constant, initial pressure. So my first boundary condition it goes by P when it goes to infinity, and any T it will be equal to PI. So initial condition, the boundary condition. But the second boundary condition is actually in the center of where by radial flow, we can assume like this. I think we covered this from the chapter 4 when we first discussed about the Darcy equation, the radial flow. And here's the trick. We assume this RW, which is the wellbore radius, is much smaller than RE, is the reservoir extent. So for the precipitation of the solution, so to make the solution more simple, we actually use instead of the R goes to RW, we says R goes to 0. So meaning we assume that this wellbore is just like a single line, so it doesn't really have any radius size. I mean, when we talk about this radial extent, which is really, really big, and then just talk about this RW, which is much, much smaller than the entire extent, this RW is almost look like almost 0. So we can just simply assume that R go to 0, then satisfy this Darcy equation, radial flow Darcy equation, and this assumption is called line source assumption. So we have these three boundary condition answer as initial conditions. Then we are going to come up with a very awkward variable here. This is called, by the way, Boltzmann transformation. So we are going to define the S, this is a new variable, as R square over 4 eta t. I mean, the point is that PDE just is too complicated. We want to make this PDE problem to ODE problem. So PDE meaning that the pressure used to the function of R as well as T, but by having this, it looks almost like a random or ambiguous variable, but by having this can be written as function of S. So now we only have a one variable, so it become an ODE, which used to be PDE. So and then the PDE ODE is much simpler. If we have a such variable, then we have to from this equation. We have to replace all the R T with the S. So, and we are going to do this by step by step. So let's see. What's partial S over partial T, which we have here, right? We have here. What's this? Yeah, we have a D S right here, so it's equal to minus R square 4 eta times T 1 over T square. And this is equal to minus S over T, right? Likewise, we also want to have what the partial S over partial R. So if we take the derivative here, then this become 2R over 4 eta T, and that's equal 2S over R. Yeah, that's it. So by having these two, this one, we can definitely replace this one as well. Now we need this one. So we have to take a derivative with respect to R one more time. So if I take the second derivative, right? Second derivative. Oh, okay. Okay, I will stop here. So in the equation, as I said, we have this one and this one and this one. And we are going to solve it in the order of, so this one will go first, and the second, and the last. And in doing so, we are going to use these two equations. So first, we have to convert partial P over partial T. This is equal to partial S. We can switch the denominator. That will end up with a dP ds times partial S partial T. Please note that I use this D, not the partial, because when we take the derivative, take the derivative to P with respect to S, this P is now only the function of S. So we don't need to use partial derivative here. So it's a small d, not the partial. And the second term here is given in the above equation. So it will be dP ds times we have here minus st, right? So if I make it in the order, then it will be like this. And the second equation, we need to have this. That's partial P, partial R. Again, we are gonna make it dP ds partial S partial R, and we know this partial S over partial R is equal to this. So it will be same as dP ds. Lastly, we also need a second order of derivative to get this part. So if I may continue, again, we are going to apply the chain rule here. First, we are going to apply the derivation to this part, then this part. So partial R 2s R times dP ds plus 2s R times dP ds partial S partial R. If I may continue, we know this one will be 2s over R. So the second term is done. So this part is done. But we need this. So let's say this one as A. So I'm gonna solve this A. This is equal to minus R squared 2s plus 2 over R times partial S partial R. And okay, we know this is equal to 2s over R. So what we have here is equal to 2s over R squared. If we took it back to the above equation, then we will get partial P, partial R squared is equal to 2s r squared times dp ds plus 4s squared over r squared times dp second derivative of with respect to s. So let's say this is equation 2, equation 3, equation 4, and this equation is number 1. So by replacing equation 2, 3, and 4 into equation 1, what we will get is two s over r squared dp ds plus 4s2 over r squared ds2 squared plus 1 over r times 2s r times dp ds equal to 1 over eta times minus s dp dt. As a reminder, this is equal to this, and this is equal to r partial p partial r, and then lastly, this part is equal to 1 over eta times partial p partial t. And we just replaced every t and r by the new variable s. And then we can clean it in such way if we organize it. And we are going to multiply by r squared over 4s in both hand sides. Then what we'll get? S dp ds plus dp ds, and right hand side there will be minus 4 eta t r squared dp ds, and also recall the s is defined as r squared over 4 eta t, so this become s. So we will get, again, it's a long equation, but or we can also written it in this way. So we are now halfway. We are now on a halfway for the solution of the equation. Wonderfully, we just convert PDE, which is challenging, into ODE. Now the P is only function of S, and then it looks very simple. So we successfully turn into ODE. And then this is second order ODE equation. So we have to take the integral twice to get the final solution. So, and then we are going to tackle it like a step by step. So let's u, this is not a really new variable, but we just want to make it u as dpds. Then what we have is s times du ds plus 1 plus s u is equal to 0. And we have to reorganize it to separate the variable. So we want to have all the u variable on the left-hand side and the all the s variable on the right-hand side. So if so, then we will have a du over u is equal to minus 1 plus s ds. This is also can be minus s over 1 plus 1 ds. Now we can take indefinite integral in the both hand side. So we're going to take the integral here and here. Um, ln u is equal to minus ln s minus s plus c1. And if you know how the logarithms and the exponential function works, then this u can be also be written as c over s e to the minus s, where c is equal to minus e to the c minus c sub 1. It's almost done, but now we have to take another integral to this function, but this function is now very challenging because as you might can see, this s and then e to the minus s is in the same hand side, and there's no straightforward way to separate this into, or there's no simple solution for this. So that's how we now are going to use the exponential integral function here, which is ei minus x. So the shape of this function goes by this. Is equal to, by definition, minus s x infinity e u u du. So in our case, this is actually this part. The variable is actually with respect to s, so you can just use the s. Because u is dp ds, that is just we compute as this, we can apply definite integral from s to infinity so that we can use this new exponential integral function. So if so, p s equal to infinity minus p s is equal to, so the constant is a constant, so we can take the constant out, and the rest of part, this become minus s infinity. So I'm gonna use different variable here, minus, which is u du. And then this part can be written as c times ei minus s. And we also put the minus in front before the c. That's because of by definition. Um, let's talk about this. What's the P when the S goes to infinity? Again, S looks defined in this way, right here. So if it goes to infinity, that means it's either R goes to infinity or T goes to 0. So this is the initial condition, and this is the first boundary condition. And if you scroll up, your first boundary condition, and then the initial condition says when the S goes to infinity, meaning either make the T goes to 0 or R goes to infinity, then it's equal to the initial pressure. So by the first boundary condition and also the initial condition, this will become PI. And if so, we can sort our equation. So now this PS, now we can say it's actually the function of R as well as T, which is combined in the S, but now we don't have to say S, so it's the same P PRT is equal to PI plus CEI minus S, where S is R squared over 4 eta T. Now we haven't solved what the C is. For this, we are going to use the second boundary condition, which was line source assumption. We have this equation. Two pi kh. If you don't remember this, then review chapter 4 of the book. So if we have this, and also this R should replace by the S. So this partial R, partial P partial R is equal to dP ds times partial S, partial R, and this one we had it earlier, so this become 2S over R, right? Yes. So if we have this equation, then replace this part with this, then we will get limit R is equal to 0 or S equal to S goes to 0. We have 2S oh, wait a second here. This was U. So and we have the solution for the U above, which is this. So we are gonna replace U with this equation, and that will become C over S times e to the minus S times 2S R, and it's equal to 2C over R times e to the minus S. Then now we want to replace this equation into here so that we will get limit R goes to 0, meaning S goes to 0, and we have R times 2C over R e minus S. So the R is gone. So now we don't have to care of the R. So 2C times e to the minus S is equal to Q mu 2 phi KH. And obviously when this S goes to 0, then this one become 1. So we have C is equal to 4 pi KH Q mu over 4 pi KH. So by fitting this C into here, the final form of the solution is finally PRT is equal to PI plus Q mu 4 pi KH. So I simply replace the C with respect with this above second boundary conditions outcome, and the EI times minus 4 KT porosity, compressibility, viscosity, square. So this is the outcome. And typically, the exponential integral function, this is lower than 0. So meaning as time increase, as time, so the P is always lower than the PI. That makes sense, right? So once this Q, if the Q plus means we are producing the fluid, so when we take the fluid from the subsurface, then the pressure will be deflated. It will be decreasing. So that's whole point. And this is very generalized form of the solution. So basically this function show you every location, every time solution, but in the well testing, we can only get the sense of what the pressure in the bottom hole, meaning we typically only need this one. So when the P R is equal to the radius of the radius of the well bore and T, we call it this bottom hole pressure, and this is only the function of time, and this is equal to Pi plus Q mu over 4 pi kh, and the EI is 4 kt RW squared. And when we put this RW, which is again very small number with respect when you compare it with it to RE, the entire input is here will be very small number. It's very small number. So when it's close to 0 or very small, so there's a alternate way of explaining this in an approximation. So it says when the x variable is close to 0, then not just close to 0. Okay. Yeah. When it's close to 0, the EI minus x, which is this function, can be written as this is approximation. So this is the Euler Mascheroni constant. It's a Euler Mascheroni constant, or Euler constant in short. And this is equal to 0.5772 dot dot dot, and plus ln x. So with this approximation, and this will be turned into PWF T is equal to PI plus Q mu 4 pi KH. And then here we have this approximation. So and this approximation can be also be written as, so this is equal to ln x times e to this Euler constant, right? And this is equal to I would say gamma prime times x. This is now equal to 1.781, which is e to the gamma, e to the Euler constant. Okay. This is equal to then 4 eta t over times r w square. And again, this is the like a negative number, so we can switch the numerator and denominator by changing the sign of this log. So this can be pi minus q mu over 4 pi kh times, and then 4 eta t over gamma prime times rw square. And again, this number is equal to 1.781. And this is it. So this is the final solution goes by this. This is fine. This is final solution for the transient flow. But in a special case, if we want to get the how it changes and the approximation of the outcomes, in the well-bore, we have this equation, and this particular equation will be used in the interpreting the well testing, which you will discuss in chapter 7. Okay. To summarize, we had a simplified diffusivity equation with 7 underlying assumption, and among these, we are gonna solve it in a transient condition. And the transient condition is when we are doing the well testing or PTA, pressure transient analysis. But this particular equation is the PDE, so now we have to convert into ODE. Before doing so, we summarize what their initial condition as well as boundary conditions here. And by using this Boltzmann transformation, we could enable turn this PDE into the ODE, simpler, straightforward. So, and if so, we can get this simplified ODE in the end. But here again, we have a very awkward S, which is new variable. It's quite seems to be random and very complicated, but in the end, it make it much easier. So let's do this, and this is second order ODE, so we have to solve it step by step. First, we take the variable split separation, and we apply the indefinite integral where we end up with this constant. And again, we have to the additional integral to the outcome, but this form is quite not straightforward. So that's how we use this exponential integral function, which is EI minus X. So if we have this function, then we can now explain the final solution in this way. This left-hand side, on the left-hand side, when the S goes to infinity, this is the same as the initial condition and the first boundary condition of PDE. So we know that this is a PI, and this one is actually the actual pressure. So we have this, and by using second boundary condition, we could know what the C is, the constant, and this is the final solution for any location, any T, and up to here, it's the most generalized solution. Then we specifically want to know what the pressure in the wellbore location, because when we do this well testing, we can only measure the pressure in the wellbore, not anywhere else. So and we call it PWF. I think the PWF meaning where and then the flowing. So when the fluid is flowing to the where, so I think that's how the WF. So this can be used. This can be approximated to this logarithm function, and we have the final expression of the variable pressure over time. And this will be used again in the PTA, pressure transient analysis. All right, I think this is what we have today, and good luck.